Okay, to begin with here, we're going to be talking today about infinite geometric series. And what we learn is only applicable to geometric series. What we learn has no place in a discussion of arithmetic series. Okay? So when we talk about convergent series or divergent series, we're talking about convergent geometric series or divergent geometric series. And it turns out that only one of these, convergent, only one of these can we solve problems with. What I'm telling you is that if a geometric series is in fact divergent, there's nothing we can talk about in terms of the infiniteness of this thing. But if it's convergent, we can talk about the infiniteness of this thing. To begin with, as a warm-up, I'm giving you two series. Convince yourself that they are geometric. And if you can convince yourself that they're both geometric, then you ought to be able to write the value of the common ratio. Common ratio is 1/2 here. Would you agree? That I multiply 2 by 1/2 to get 1, I multiply 1 by 1/2 to get 1/2. That means the next term would be 1/4, then it would be 1/16, then it would be 1 over 32, 1 over 64, and the bottom of the fraction would continue to be doubled, causing the whole thing to become half as great. Whereas the common ratio here is 2. And that's obvious, right? Okay. What we are asked to do is find the sum of the first 4 terms in this first geometric series, and then the sum of the first 5 terms and the sum of the first 6, and etc. Now, how can we do this? Well, I guess what I could do is I could take a brute force approach. And I could start writing out, what do we want to get to? S10. And I could, what am I at? 6? And I could write 4 more terms and I could add them up. But I think that gets tedious. First of all, notice that the sum of the first term is 2. And then the sum of the first 2 terms is 3. It's half as great. And then it's half as great compared to the second term. So S3 is 3.5. And if we add 1/4 to that to get S4, I'm going to work in decimals. And the decimals may get quite long, so they may run past your table. 3.75, that's to here, right? This is S4 to here. So if I want to find S5, I have to take that 3.75 and add what turns out to be 0.125. Okay? 1 over 8 is 0.125. So 3.75 plus another 0.125 gives me 3.875. But I hope everybody understands how tedious this is going to get. Tedious means just tiresome, wearisome. Why would we do this? Instead, we know, everybody, that Sn is the first term, which we know, times the common ratio to the n minus 1 over the common ratio minus 1. Well, why don't we go table building? Why don't we use our table features of our calculator and put this expression in with the numbers, and we'll put the numbers in first before we start plugging stuff in. And then we can just go to our table, and the answer to the question will be staring us in the face. So I'm going to put in T1, which is 2. So I get 2 times R. I think it'd be more convenient for R to just be written as 0.5. Rather, if I put 1 over 2, then I have to put an additional set of brackets somewhere. It's going to get cluttered. minus 1, and it's over r, which is 0.5 minus 1. And this, I'm not going to rewrite the whole thing to point out to you that the denominator here is negative 0.5. So I can put into my calculator, again, we're going to go y1. I've got some stuff there. Clear it out if you do. 2, and then in brackets, which means multiply by 0.5 raised to the x, minus 1, n bracket, divided by negative 0.5. So what I have entered in is something where n is x, and then if I direct my table to start with x being 4 and going up by 1, I got my table. I got my table generated. I'm actually going to go to my table setup and start at 1 and go up by 1 to demonstrate to you that this works for all the sums. So when I go to my table, what is the sum of the first term? So just focus your attention up here, and you can see that S1 is 2. Well, of course it's 2 because that's the first term. S2 in my calculator is 3. Well, that's 2 plus the 1. Then we've got 3.5. Okay. And if you add up the first 4 terms, so this first number here is S4. And if you look, S4 is 3.75, 3.8. Okay, so let's just fill in these. So, man, oh man, 3.9375, 3.96. I can tell you right now, because I'm familiar with these numbers, that this will be actually 3.96875, if anybody really cares. And you can prove that by going over here. Not that it matters. This is not the point, okay? 3.96875. The number's getting bigger. The number's getting bigger because we keep adding something to it, right? All right. Let's do the same thing here. So this number would be 16. And we could write S4 by adding 2 plus 4 plus 8 plus 16 and getting, and then 62 and 126 and 5, 254 and 510, 1022, 2046. We're good? So we have 2 geometric sequences in which the sum is getting larger each time, right? This continues to get larger, and this continues to get larger. I hope you understand that how this is getting larger is different than how that's getting larger. Intuitively speaking, you understand there's a big difference here. Okay, let's answer this question now. What happens to the sum of the terms in each of the 2 series as n approaches infinity? So let's start with series 2. As n gets bigger, that's all this statement means. It means, let's just keep exploring. Let's take our calculator for series 2, and let's just keep going. As n gets really large, what's happening to the sum? The sum is exploding, right? It's doing this. As n gets bigger, this is taking off to infinity. So as n approaches infinity, the sum of the terms approaches infinity. By the way, that is called divergent. We'll define it later, but I might as well put it here now. This is divergent. With series 1, as n approaches infinity, the sum, it actually approaches a number, which is a really bizarre outcome, that you're going to add up an infinite number of things, and there's a fence that sum never gets past. And it turns out it's 4. Let me demonstrate that to you. I'm going to put in the original sequence, series, whatever you'd like to call it. Correct me if I'm wrong, was it 2 times 0.5 to the n minus 1 over negative 0.5? Pretty sure. So when I go to my table here, I mean, it's saying 4. I'll come back to that. Look at this, 3.9999. It turns out it's not actually 4. It just keeps getting closer and closer and closer to 4. And there's a reason for that. It can't reach 4 for the following reason. You are starting off, I'm going to call this distance 4. You are starting off and you are taking the number 2, which is half of this distance, of 4. And then what you are going to do is add half of that 2, which is half of the remaining distance. And then you're going to add half of that 1, which is half of the remaining distance. If you keep adding half of the remaining distance, then theoretically, you never get to the end, do you? But you do at infinity. This is what we would say. At infinity, the sum converges to the number 4. So this is convergent. Right? So, convergent, as n approaches infinity, Sn approaches a value, a number. We can talk about the sum of the infinite number of terms. This graph I'm going to show you, you don't need to write it down. But I'm going to use it just in an explanation here to explain why we call this convergent. So this is 4. When n is 1, the sum is 2. When n is 2, the sum is half that distance towards the 4. When n is 3, it's half as well. When n is 4, it's half as well. So what's happening is that sum is getting closer and closer and closer to 4. And that's what the word converge means. It means to get closer. If you have traffic coming off of a ramp on a highway joining the mass of people driving, we say that things are converging. They're getting closer together. So this graph would actually look like the following. And it would just get closer and closer and closer and closer, but it will never reach. On the other hand, what's happening here, if this is n, oh, by the way, this is Sn. This is Sn. Here's the sum at 1. Here's the sum at, I'm going to run out of room right away. Here's the sum at 2, at 3. It just keeps getting bigger and bigger. It explodes. It's diverging. So divergent is as n approaches infinity, Sn also approaches infinity. Okay, example. The first term of a geometric series is 3 and the common ratio is -1/5. Is this convergent or divergent? Well, you know what? There's only one way you can answer that. It's to put the formula for Sn into your calculator and go to your table. There's only one way you can answer it now. In 5 minutes, there's an easy way to answer it. The answer is going to be it's convergent. Okay? But I'm going to put into my formula the value of the first term and the common ratio. So Sn is the first term times the common ratio. Now we do need a set of brackets around this because it's negative. Raised to the n minus 1 over the common ratio minus 1. Same thing we did in the warm-up. Okay. So I'm going to put that into my calculator, and I'm going to start exploring my table to find out, is the sum getting bigger and bigger and bigger, or is it approaching something? So 3, and then this is tricky, in brackets, and then another set of brackets, negative 0.2. Can you confirm that negative 1 over 5 is negative 0.2? Okay. Close the brackets, raise that to n, which is x, subtract 1, close the brackets on the entire top, and then divide by negative 1.2. I suppose I could put a set of brackets and then go negative 0.2 minus 1. But negative 0.2 minus 1 is negative 1.2. I know I've been scrolling around, so I want to start at 1, not 13. Okay. Double check to make sure I've entered things correctly. First term in brackets, common ratio to the n minus 1, close all the brackets. Okay, we're good. So I go to here, and the sum of the first term is 3. And if you multiply 3 by negative 1/5 and add that to 3, it turns out that you will get 2.4. So the reason why the sum has gone down is the second term is negative. Like, think about that for a second. The second term is negative because of the negative common ratio. So S1 is 3, and then when you add that negative second term, it gets less than 3. And it becomes 2.4. And then when I add the next term, it goes back up because the next term's positive. And the sum is going to wobble up and down. But I want you to notice it goes from 3 to 2.4 to 2.52 to 2.496, that these numbers are oscillating up and down over the number 2.5. Sooner or later, I mean, it even says 2.5 there, but sooner or later, my calculator, and it happens right there, my calculator is going to crap out on me and say, you know what, it's 2.5. It's not. If we could show more decimal places here, we would discover that it goes from being a little bit less than 2.5, and here it's actually probably 2.5, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, or something, okay? So this is convergent. It's converging on 2.5, but it's not converging in the same way the other one did. It's doing this. This is 2.5. The sum goes from being 3 to 2.4 to a little bit more than 2.5 to a little bit less than 2.5. It's doing this. Let me draw that for you bigger. What's happening is, here's where 2.5 is, and the graph is doing this. Does that make sense? Something funny? Somebody out there? Blame somebody else, sure. So this is convergent. It's convergent on 2.5. And all I mean is, rather than me writing as n approaches infinity, Sn approaches 2.5. And what we would say is the sum of the series is 2.5. Okay, this is all going to come together real soon, because we're about to say I don't need to use my calculator anymore. And you don't. If a geometric series is convergent, you can find the sum with this formula. Okay? If. What did we say the sum of this was? 2.5, right? The formula says S equals the first term over 1 minus r. Not Sn, because n is infinity. Go ahead and take the first term in this and divide by 1 minus r in brackets. You get 2.5. You don't need to use your calculator to find that sum. But you might need to use your calculator to determine if it's divergent. Because, and I just want to highlight this right now, that works if it's convergent. If it's divergent, there is no sum. You have no business talking about the sum of an infinite number of terms unless it's convergent. So, how many of you suspect that this will be convergent? What is it about this that tells you I think it's going to be convergent? Who wants to stick their neck out on that? Whereas this will be divergent. It's multiplying by a number smaller than 1. You nailed it. If the common ratio is smaller than 1, it's convergent. And we'll formalize that in a second. But let's just say that you already know that. I want to shave a couple of minutes off this lesson. Let's not put this into the calculator to prove it's convergent. It's convergent. And basically it's convergent because if r is less than 1, and there's more details to that we'll have to talk about, then each successive sum, you're adding a smaller number. So it's not exploding. It's settling down to something. So S equals the first term over 1 minus r. Well, you have to figure out what r is. Kale?
Negative 2. Or not negative 2, but 2. Divide by 2.
No.
5.
No. Well, divide by 5, which means r is 1/5. Right? So you're dividing by 5, but that means r is 1/5. So that means we get 10 over, I believe, 0.8. You can double check that arithmetic. 0.8 is 4/5. I want to say 12.5. Okay. Quickly, you don't need to do this. Sn is the first term, which is 10 times in brackets 0.2 raised to the x minus 1 n bracket divided by bracket 0.2 minus 1. I'm not using the formula we just learned. I'm using the Sn formula. It's approaching 12.5. But you don't need to do this anymore, okay? How are we going to answer B? We're not, because there's no answer. It's divergent. We can't find the sum. If you use that formula that we just learned, you'll get a number. But it's obviously going to be wrong, because the answer to this is infinite. It goes on forever. It's divergent. Okay. So now let's tie it all together. You guys still with me? Am I going too fast? Okay. Rather than going to our calculator or starting to add them up and go, 12.49, 12.499, rather than doing that, the rule, and it's been nailed, except, I think you said r was less than 1, right? Okay. Well, r has to be less than 1 or greater than negative 1. It has to be between negative 1 and positive 1, not including negative 1 or positive 1. And 0 is a number between there, and it can't be 0. So what I am saying is the common ratio needs to be a number that lies between negative 1 and 1, but cannot be 0. And then it's convergent, and then you can use the formula. We can write that this way. This statement here means the following. It means that these are the values of R. These are the values of R that make it convergent. Can be a number bigger than -1, less than +1, but not equal to 0. So these open dots mean not equal to these numbers. Are you with me on that notation? To how many of you, and I'm just curious, is this notation perhaps seems new to you? You learned it, but it's not, you got to really reach back in your head. Okay, that's fine. And we'll use it more and more often. So if that's the case, it is convergent, and you can find the sum using that. So is this convergent? Sure. -1/3 is basically, forget the negative for a second, is it a number smaller than 1, but not 0? Yes. It's just that that -1/3 is over here someplace, right? Okay. So this is convergent. Can we find the sum? Yep. Notice, by the way, it's 1 minus R, and in your other sum formulas for Sn, it's R minus 1. This is child's play. I would like you to figure out what that is. It's going to be 5 over 1 minus -1/3, which is 4/3, which is 15. Oh, I'm going to say 3.75. Okay. So if you went to your calculator and went table hopping and you kept going down, you'd see it encroaching on 3.75. Done. There's nothing we can do with this. How many of you know what these symbols mean in math? So if I had that, do you know what that means? Turns out it's called the absolute value, and what it is 12. We have a unit on absolute value later in the course. So what we can do instead is say that the absolute value of R has to be between 0 and 1. Forget about negatives. If R is -1/2, the absolute value of -1/2 is 1/2. It's between 0 and 1. This is convergent. This is not convergent. And I'm just pointing out this notation because I might slip, even though you haven't been taught it formally. I might slip from time to time and use it by mistake. And I might not even realize I'm doing it. So in the end, this is a nice summary of things here. It's a very nice summary. It tells you when you can find the sum because it's convergent, and when you can't because it's divergent, and it tells you how to find the sum if it's convergent. So I think you've got about 12 or so minutes left in class to try some of these. And Sukhman, we'll start tomorrow's class by going over a couple of those questions you were wondering about. Of course.